Okay, welcome back. We're gonna push ahead with our rest of the agenda for today. So we're going to kick off with the theory session for classical machine learning, followed by a hands-on session for classical machine learning. And then we have a panel discussion at the end of the day. I'm going to hand over to my colleague, Dr. Amna Asif, who's going to be chairing the next sessions.
Thank you, Nasir. Hello, everyone, and welcome back from the coffee break. My name is Amina Asif, and I'm a research fellow with Professor Rajput at Tissue Image Analytics Center. I'm currently exploring applications of weak learning in computational pathology, and I'm delighted to chair this session on machine learning. In this session, we'll have an introductory talk about classical machine learning, followed by a hands-on session for demonstrating a classical machine learning pipeline in computational pathology. The first speaker will be Dr. Abhir Bhalerao. Dr. Bhalerao is a reader in computer science and co-investigator of the PathLAKE project at Warwick. His research interests include image representations and machine learning for applications to medical diagnosis, especially radiology and histopathology. He was a co-founder of Warwick Warp Limited, a tech startup specializing in biometric technologies. He will be speaking about some introductory concepts in machine learning, illustrated with some examples from computational pathology. If you have any questions, please post them in the Q&A section on Zoom. Over to you, Dr. Bhalerao.
Thank you, Amna. Can everybody hear me okay?
Yes.
Okay, I'm going to start sharing my screen now. Let's hope this works. Okay, right. Okay, so it's shared the wrong screen, but here we go. Good afternoon, everybody. So my talk's going to be about image features, images, and classical machine learning. So I know in the program it just says Introduction to Classical Machine Learning, but I wanted to include some background into how we get the sort of the important data into a machine learning pipeline. Okay. So I'll be covering the basics of how images are represented. This is in terms of for computation. I want to talk about what we mean by image features and what are image features, and how they can be extracted from images. So I'll be talking mainly about color, texture, and shape type features. So these are the most important things, particularly for doing computational pathology. And I'll also be introducing you to the ideas behind two classical machine learning methods, probabilistic methods and linear classification. So let's start with some fundamentals. So there's been a lot of discussion today and some great talks where people have talked about the whole slide images, but what exactly are they, and how do we represent them for the purposes of computation? Well, we can think of images as grids, and one sort of definition is as a matrix. So if you're a mathematician, you might call it a matrix. I know in biosciences people use the term matrix as well. And another is as an array. So if you're a computer scientist, you talk about arrays of pixels or pixel values. And these represent the amount of reflected light which is captured by a digital camera. And so we're all familiar with digital cameras. So cameras use lenses to focus the image that they're taking the light from the scene onto a small sensor, which actually contains the grid that's captured. So typically, if I have say a digital camera, say a phone camera, I may be capturing a 4K image. So a 4K image is actually 4K by 3K, an array of pixels. So that's why we talk about, say, 12 megapixel resolution. So something like a modern phone camera will capture that sort of resolution. Whereas in digital pathology, we're using, in addition to the standard sensor, we're also using some form of microscope lenses to focus in on particular regions of a digital slide. And that the magnification of that will change. Now, the other important difference between, say, taking an image of the camera and taking an image of a slide, a histology slide, is that, of course, we're capturing things which are essentially two-dimensional. And the magnification can result in images of much greater size. So instead of 12 million pixels, we'll be capturing images of the order of, say, 60,000 pixels in each dimension. And this is because the actual calibrated pixel resolution is much, much smaller. So 0.25 microns per pixel is typically captured. So let's have a look at the sizes. So the size of the image does depend on the magnification. So if I have, let's have one example here of a 40x magnification. So that gives you 0.25 microns per pixel. So if my slide area is 45 millimeters by 15 millimeters, which is typical slide area, we end up with the order of 180,000 by 60,000 pixels. A second example, if I change the magnification to 10x, I end up with 1 micron per pixel, and that results in a slightly smaller resolution in each dimension. So there's a factor of 4 reduction. And if I'm scanning an area of 15 by 15 millimeters, then I'd end up with 15,000 pixels in each dimension. So the raw uncompressed data that is captured requires 3 bytes per pixel. So the scanning system will use color filters to produce the different channels that we see. So the uncompressed data is actually quite large, and there was some talk today about the sizes of images that are produced by these scanners. So uncompressed is quite large. So the first example is 32 gigabytes, and the second one will be smaller. But they're still much larger than you would normally see in medical imaging. So, for example, CT scanners don't produce anywhere near this size of data. But of course, we have compression, and that gives us data compression reduces these sizes down by factors of 10 to 50. So that's where we get something in the order of a gigabyte of data for a whole slide image. So let me talk about features. So before we can actually do any machine learning, we have to extract features. So what do we mean by features? Well, features are something about the data samples which we can measure. In this case, of course, our data samples are images. And in some way, they summarize information within an image that allow us to classify the sample. And we can think of the machine learning task, or machine learning in general, as a collection of computational techniques which associate features which we extract from the images with outcomes, what we call class labels. So you would have heard the term weak supervision, or weak machine learning, or supervised learning. So in supervised learning, you're going to use annotated samples or annotated examples to learn the feature label association. There's also another form of learning we can do, which is called unsupervised learning, and it may come across that, where we don't have necessarily annotated samples, but we study the clusters of features and treat them as distinct classes. So what I'm going to do in the remainder of the talk is kind of go through this pipeline. So I've said something about the input data. So on the left-hand side, we've got what I've called X. So it's a collection of data samples. So in this case, I've labeled these things X1 to Xn. So these could be images. And then associated with each of the images, we're going to create something called a feature vector. And there's one per image. And these are then fed into a classifier, which is the form of a function, a parameterized function, which then associates the inputs with labels. So here, the labels I've labeled Y, and there's a label Y associated with every X. So for example, we may have patches of a whole slide image. So these could be the input samples. In this case, I've taken an example from the Chameleon data set. So these patches, the task here was to use these to work out whether the label, whether the patch you're looking at was malignant or benign. So each of these input patches of the image or tiles has an associated label with it, and we can represent that with a 0 or a 1 in the output. So what should the features be? Remember that I said that there's one feature vector or one feature associated with each input. So what should these be? Well, we can't use the image values on their own. So typically we run some sort of computational algorithm on the images to generate features. And we take groups of local pixels or pixels in a small region and tend to build a feature around that to be used by the classifier. And it turns out that if you can actually separate out important structures from the background, what we call segmentation, we might be able to take measurements from these things, such as area and shape. So I'm not going to say much about segmentation in my talk, but that is one way to actually allow us to for example, produce morphological features. And we can also summarize color distributions or the local color as distributions and use those as features. We can use image filter operations, and I want to introduce you to the idea of running some sort of filter operation on groups of pixels to allow us to characterize patterns that we see, such as texture. So what are the kind of properties of features we're after? Well, features should be local, they should be distinctive, and in some sense they should be invariant to rotations and intensity variations. Okay, so let's look at the first example, which is histograms of color. So these are the kind of the simplest things we can do, is to find out what is the distribution of colors of a given region of an image. Well, you're all familiar with this histograms, I hope. Well, we're going to count in this case, in this histogram, the frequency of colors. And here's an example. So I've taken some of my patches of my problem. So I'm going to try to distinguish these patches into whether they are malignant or they're benign. But we can start by just trying to produce a histogram of the colors in each patch. So what you're looking at here is along the x-axis, we've got color, and I've shown the color as this in this key here. So we've got the sort of the reds over here and the blues on the right-hand side, the rainbow colors. And the y-axis, we've got frequency. So if we take that first image, we can see that it has a distribution sort of with blues and pinks in it. And as we go down, we can see that the distribution changes according to the image. So perhaps we could use this information and we could represent the colors within the patch as a feature. And here what I've done is I've done a little trick where I've actually quantized the colors into 64 different colors, and we can choose a quantization when we calculate the histogram for each of these patches. This sort of trick of looking at features as histograms is quite useful, not just for color. It's a kind of nice general way of taking any sort of feature that you calculate from an image and looking at or comparing them by eye just to see how discriminant they might be. So if we see differences in the shape of their distributions between the classes that we're looking at, perhaps they might be useful features to use. So what about texture? So how do we go about representing texture, and what is texture? Well, we all know the idea of texture, and in images, we're talking about the representation of natural phenomena. So here's some examples which I took on one of the many walks I've been taking in recent days. You've got, on the left-hand side, you've got a synthetic or a man-made texture of brick, and we can see there's some repetitive pattern. In the middle, we've got this kind of cracked mud, and this is a kind of a naturally repetitive structure because there's some randomness in it. We've also got in the middle here some gravel, so there's a grain to it. So we can see that the grain of a texture will vary depending on the size of the structuring element that we have. So something like sand will have a very fine grain, whereas pebbles will have a large grain. Texture also has directionality. So here's a picture of some grass with, you can see the stems going in a particular direction, but it also includes randomness. So in the final image there, we've got randomness. So how do I go about capturing this sort of information? So these are clearly not pathology images, but typically we will be looking to capture some sort of local changes in this textural quality of the image. So how can these be captured? Well, it turns out that there's a nice little operation which is used quite a lot in image analysis, which we call convolution. And this allows us to filter the input and generate a map, which is a sort of a way of matching what the input patterns are within the image to produce an output image or a map to tell us where these patterns are and how significant those patterns are within the image. And I'll show you how this works. It's quite a kind of simple little operation. So if I have a grid of pixels, an array of pixels, I'm calling this F. And if I take another little image, this is called a filter array or a filter kernel, and it's usually very small in relation to the size of the image. I can do this kind of special operation, which allows me to generate an output map. So how do I do this operation of convolution? Well, I start by putting the filter kernel on top of my image, and then I multiply the corresponding numbers between the kernel values and the image values, and then I sum the output. So this is the convolution operation. This actually gives me a single value. If I put my kernel in this case at the top left-hand side of the image, it gives me a single value. Okay. So how do I complete the rest of the map? Well, I have to move my filter to the next position. So I take my image filter and I move it to the next position, and I repeat that operation, which was multiplying the corresponding values and summing to the output. So this is what image convolution is all about. And you can see that I can carry on doing this across the whole input image, row by row, column by column. Of course, I need to do something special at the edges because my filter kernel falls off the end. And one thing I can do, a simple trick, is to treat anything outside of my input image size as being 0. So I end up with an output image or a map, which is a representation of the filter kernel values multiplied across the image. Here's some examples which I've run on one of my patches. Now, to remember that we've got a color image, so we'll have multiple arrays. We'll have an array for the red channel, an array for the green channel, and an array for the blue channel. So I'm going to run this image convolution just on the, in this case, just on the red values, okay? And we can see 3 different kernels that I've used, filter convolution kernels, and these images here represent the outputs. The first one is similar to the example that I showed you, where all the values in the image kernel were the same. So in this case, all the values of 1. And what this does is to blur the input image. Okay, so why would I want to blur the image? Well, there may be a reason to blur it. The middle one is interesting because this particular kernel highlights vertical edges in the input image. And the last one is a little bit strange. It has this kind of center surround type of appearance. So there's a very large negative value in the middle. And when I run this kernel, I end up highlighting what's known as the second derivative of the image function. But actually in sort of interpreting the image, we can think of this like a little blob detector. So it detects tiny little blobs, which are similar in shape to the input kernel. Okay. So going back to the problem I had about texture, how do I go about representing texture? Well, it turns out that I can use a special set of image kernels that are known as Gabor filters, and they have the property of being able to find not only the directionality of any features in an image, but also their frequency. And they consist of these rather interesting waves which travel in different directions and change in frequency. So if we look at the bottom row, for example, focus on the bottom row, we can see that these bar patterns rotate around the circle. And I run all of these little feature kernels on my image, and I will generate maps for each of these. And these are known as Gabor filters. And if you're interested, they're actually created by multiplying the cosine function with a window function, a Gaussian function. So we end up with this kind of weighted wave. Okay, so what is this, why is this important and why would we want to do this? Well, it turns out there are some very similar types of functions which are done within our human visual system. So this Gabor filters have been shown to be the functions that some of our special cells within our visual cortex do exactly the same thing. And it's a way of creating features. So here I've run a quick example. So on the top one, I've got top row, I've got 3 images, and I've taken 2 of my filters and I've run them to produce maps, which are the Gabor filter outputs. These are the feature maps. So on their own, they don't look very exciting. It's when you put them together that you find that they will capture particular characteristics of the different images. And you can already start to see with that first row that the 3 images, the image maps, look very different. Okay, so so much for filtering for texture. I mentioned that we can also use, look at shape or morphological features. Now, to do this, we obviously need to actually segment out particular structures and then calculate these features. So if we can delineate cells, cell boundaries, we can measure morphological features. So here's an example here from the TCGA where a particular operation has been run to highlight the cells. And then we can start to take measurements of individual cells in terms of the shape or morphology. So for example, we can take measurements of area, we can take measurements of eccentricity, which is this ratio of the smallest width against the largest length that we can find across the cell. We can also look at its deviation from a circle, and that tells us something about how much it is got elongated or strangely shaped. And another thing which was, I think, mentioned in one of the talks this morning was this idea of looking at the distribution of these cells or the density, for example, abundance measures. Okay, so much for actual features. Let's talk about classification, which is an important part of the machine learning pipeline. So we've got now some features we can play with. So maybe we have texture features and we have color features. So we're going to put them through the classification stage and then end up with some sort of decision at the end of it. So how do we do that? Well, before we complicate things too much, let's look at the problem if we only have one feature. So how would we go about making decisions on a single feature? Well, it turns out we can do this probabilistically. So for example, if we have a whole slide image and we have 2 types of outcomes, one which is benign, one which is malignant, let's assume that we're given many expertly labeled regions and we extract some single feature from each region, okay? We can plot the distribution of the feature value against the outcome. So this is kind of looking at the histogram of each of the input data against which class they fall into, which outcome do they fall into. And we might get something that looks like this. So this is similar to the color feature plot I showed you, but here I've only got a single feature. So I'm looking at the kind of the outcome probability. So the x-axis is the feature and the y-axis the probability given one of these 2 outcomes. And we can see that if we choose a particular feature value, we might be able to distinguish between those input samples which are benign and those which are malignant. So how would we do that? Well, we could use this decision rule, which is say, what's the probability of the feature given that the input is benign? And is it greater than the probability of the feature given that it's malignant? Okay, and we can do that straight from looking at the histogram and choosing the right decision threshold on that feature. Okay, now this is kind of making an assumption, and it's important to know that what assumption this is making. The assumption it's making is that the malignant and the benign class are equal within our data when we produce these histograms. Okay, and what else can this tell us? Well, it can also tell us where, for example, we've got true positives and true negatives. So these are the areas under the 2 curves. and, for example, where we would make mistakes. So if something is benign and we're going to put that threshold threshold here on that feature, we're going to end up with a small number of benign cases being classed as malignant when they're not. So these are the false positives. And similarly, we're going to have a number of malignant cases which are going to be classified as benign when they're not. So these are the false negatives. Okay, so we have these sort of terms that I'm sure you'll come across: true negative, true positive, false negative, and false positive. Okay, but if our classes are imbalanced, what can we do? Well, it turns out that there's a nice little trick we can do, and it's related to a very, very old theorem in probability. So if our class is imbalanced, then the expectation that we have a benign sample or a malignant sample is not equal, okay? And the chances of getting that will depend, of course, on how many of those we have in our training set, okay? So it's a bit like choosing, say, jelly beans from a jar. If I was going to do this with my eyes closed, you know, which color jelly bean would I get? Well, it depends on how many there are in the jar. If they're all equally represented in that jar, then I don't know which I'm going to get. I'm going to get one at random. But if, for example, there are more red than blue, then there's chances that I'll get a red one. Okay. So how do we incorporate this bias into our decision test? Well, it turns out there's a very nice rule to do this. It's known as Bayes' rule. You may have come across it. Here's a neon sign that I found somebody had made with Bayes' rule on it. I think there should be more signs with mathematical functions on them in the public domain, but they're not. Okay, so how do we use Bayes' rule to make our decisions? Well, we have to turn our decision slightly the other way around. We have to find the probability of the outcome given the feature. Remember, we used this distribution where we have the feature probability given the outcome. Well, we need to calculate something different. And it turns out the Bayes' rule factorizes this exact thing known as the posterior probability. So it allows us to represent the probability of the outcome given the feature value as a product of the prior probability, which is the probability irregardless of the feature value, and the likelihood which we can get from a histogram, for example, or estimate that. And it makes this strange assumption, which is to do with the independence of the features. So if I have multiple features, how do I use this? Well, I'm looking for the outcome posterior, given a set of input features. And I have to factorize this out. And this is known as the naive Bayes decision probability. So it's this product of the prior and each of the individual likelihoods of the features given the outcome that I'm interested in. Okay.
I'm sorry for interrupting here, Abhir. If you could just wrap up your talk.
Yeah, I will do. I will. I'm just going to come. I'm going to wrap it up. So I'm going to skip the linear stuff. Yeah. Okay. Okay. So in terms of going back to our decision problem, how do I do that? Well, with the Bayes probability, I need to do this by doing the posterior probability. So I use the decision rule, including the prior. And so I'm going to skip the linear classification. I think it's going to be covered a little bit tomorrow by Fayaz. So we'll skip this. I'm sorry about that. I'm just sort of run out of time. So in terms of how we measure the quality of the machine learning algorithm, well, I mentioned the idea of these separating out parts of the results that we get into, say, true positive, true negative. It turns out there's a number of measures we can make on that, and some of these were discussed already when the results are presented, such as accuracy, precision, and recall. And there's one which comes up quite a lot, which balances precision and recall, which is called the F1 score. So going back to my problem, so I took a number of example input images, and I compared the classical, 3 classical methods for classifying the inputs in terms of malignant and benign. And what we can see, so these are not brilliant results, but they're quite interesting, because if we look at the 3 methods that I've used here, so I've used the naive Bayes classifier, I get an accuracy of 0.6, an F1 score of 0.7. Whereas if I use two other methods, which I'm afraid I didn't have time to cover, I was going to look at linear perceptrons, I get a slightly improved accuracy up to 0.7. And this is, of course, using just very, very simple feature ideas, using color and using my Gabor features. So I'm sorry I've run out of time, but I hope that you've had a little taster of what you can do with images and features and some basic classification methods. So I'll stop there and thank you for your attention.
Thank you, Dr. Bhalerao, for the excellent talk. We have a question from Joy, but it would be great if you could respond to them in the chat, in the interest of time.
Sure, absolutely. I'll have a look at that. It's very hard to see any of the chat windows when I'm presenting.
It's there in the Q&A section. Thank you. Thank you so much.
Thank you. You're welcome. Moving on, we now have a hands-on session on machine learning pipeline by Dr. Scott Doyle and Dr. Andrew Janowczyk. Dr. Scott Doyle is an assistant professor in the Department of Pathology and Anatomical Sciences at the Jacobs School of Medicine and Biomedical Sciences at the University of Buffalo in the USA. He holds a PhD in biomedical engineering from Rutgers University. His current focus is on building a teaching and research program for quantitative modeling of anatomy and cell biology. Dr. Janowczyk, I hope I'm pronouncing it right, is a senior bioinformatician at the Swiss Institute of Bioinformatics and a senior research scientist at the Precision Oncology Center of Lausanne University Hospital. He is also assistant research professor at the Center of Computational Imaging and Personalized Diagnostics at Case Western Reserve University in the USA. Thank you for presenting this hands-on session. Over to you people now.
Thank you very much. I'm excited to do this. All right, I'm going to share my screen. So the way that we're going to run this is I will sort of go through a code notebook, sections of code that I'm going to execute that will sort of demonstrate some of the classification techniques that you just heard about. Andrew is going to be fielding the Q&A session. And so if you have questions, he can sort of either respond to them or Andrew, feel free, as always, to interrupt me and ask questions or clarify things. I would appreciate that. All right, let me share my screen. So hopefully, hopefully this works is my motto. So we're gonna, I'm just gonna go through this. You should have received in the pre-session notes some instructions on how to access this drive here. So what we're looking at is a Google Drive folder that I set up for this presentation. And there's a couple different files in here, and I'm gonna go through them one by one. But basically, what we're going to do is we're going to start from the position of features that have already been extracted from a set of images. And we're going to be using a freely available data set for breast tumors. And these are sets of features that were extracted from fine needle aspirate images. So examples are shown on the screen. This data set was collected by the University of Wisconsin. And what they did was they went in for these images and they looked at morphological features of the cells. So for each image, they went in and extracted features corresponding to each cell. And then they took statistics of those features for the entire population of cells within an image. So this image represents a patient. Each nucleus had a set of feature values extracted for it. And then they took the average and the standard deviation and the worst value feature for all of those. And then that became the feature vector that corresponds to this image. So if you think back to Abhir's talk, the feature vector that he was showing going from feature extraction to classification, that's what we're going to be dealing with here. I put a link in the notebook to the website where you can look up the Breast Cancer Wisconsin data set. Again, it's freely available. It was generated several years ago, but they have access to, you have access to the feature values that they extracted, some descriptions and citations that have used this data set. And so this is what I use in my course to sort of demonstrate biomedical machine learning. When you get the data set, it looks like this. So again, during my sort of flash talk, I talked about, data can take on many forms. In this case, our form is a spreadsheet. In this spreadsheet, each row corresponds to a patient and each column corresponds to a feature. And whenever you're thinking about how to do classification, getting your data into this format in some way, shape, or form is probably one of the first things you'll end up doing when you get close to doing machine learning. All of the columns, with the exception of the first two, are feature values. So radius mean value means that this is the average radius of all the nuclei for this particular patient, texture mean, perimeter mean, and so on. And if you want to know more about how these features were extracted or what they represent, you can go through the citations here. I'm not going to do it now just for time, but you could go through these citations and get a sense of what these different feature values correspond to. The other two columns here are an ID column. So each row receives a unique identifier for that subject or for that patient. And then we have a diagnosis column. These are the targets or the outputs that we're going to be focused on. There's no units presented here. That's something that you would put in sort of the documentation for your data set. So these units could be, it depends on the feature, what the units actually are. The diagnosis label, we're going to take a look at this in a moment, but the diagnosis label is either going to be an M for malignant and a B for benign. So the problem statement is, given a set of these feature values extracted from these images, can we identify which patients have benign tumors and which patients have malignant tumors? And as I said at the beginning, when you're setting up your project, you want to sort of specify, okay, do we know or can we justify in the literature that these sets of features, these particular features, are capable of identifying benign versus malignant tumors? Are these the kinds of things that a pathologist would look for in a microscopy image to try and designate whether a patient was benign or malignant? And then we would use that as a justification for extracting these features. Okay, so that's the data set that we're going to be looking at. It is in CSV file format. It's in the same folder as our notebook. And so now I'll talk a little bit about the notebook and how we're going to be running our code. Let me just clean up some windows here. Okay, so if you're not familiar with programming, I am a big evangelist for everyone learning how to program. I think it's a really important skill, even if you're not a programmer. I'm not a professional programmer. I didn't get formal training in programming. So some of this code, if you are a programmer, some of this code is probably horrifying, but it gets the job done. We are looking at a website, a web interface to a Python notebook, which essentially is a way of executing Python code. And this particular flavor of a notebook is the Google Colaboratory, which is something that Google has put together in their suite of tools. Essentially what this will do is this interface will take your inputs, your input cells, and if it's a Python command, so a equals 5, sets variable a to value 5. If you execute this, it will send that piece of code back to a running Python runtime on the back end on Google servers. It'll compute the results of that set of code, and it'll print the results out to the screen. In this case, I didn't print anything, so I could say print a, and it'll print the value of that variable. Now, I'm not going to go through a whole programming tutorial because that would be a series of masterclasses in itself. But hopefully, if you're interested in the programming and the nuts and bolts of how these algorithms are implemented, you can take a look at this. If you have access to this from the pre-session notes, then you can go up here to File, and you could save a copy in your own Google Drive. So if you're able to view this now, this is just a view only. But if you go and make a copy in your own drive, then you can edit this and play around with it. You'll also need to download the data set as well, the CSV file. So I have a lot of text here. I'm not going to read it word for word, but essentially what we're going to do is we're going to use Python for our machine learning demonstration. It is sort of one of the more common languages for doing machine learning, both classical and deep learning. And if you're going to do things by hand, if you're not going to use a commercial package, then this is probably a good place to start, especially if you're learning programming for the first time. The core language is fairly small, but it's been augmented by a set of modules or packages that have been developed by the open source community to do a lot of useful things. And so we're going to make use of some of these packages to process our data sets. So we have a couple of different packages that help us read in some data, like our CSV file, read that data into memory and work with it. We have a numeric Python package, which is going to allow us to manipulate that data. And we have a plotting library, which is going to allow us to make graphs like the ones we were just looking at. So to use this code, we have a bunch of statements here that basically import these modules, and we give them useful names or aliases. And don't worry too much about this. This is just a series of different import steps that's going to allow us to use various functions throughout the code. So I'm going to run this. And then here, this bit of code just gives me access to my Google Drive so that I can load up the image. If you're running this yourself and you run this, then you'll get a little pop-up here that asks for permission to connect your drive to your notebook. If you're running it locally, then you can ignore this. If you're not running it in a collab, you can ignore that. Okay. So here's some details about the data set along with a link to that website that I showed you before and a summary of the features. Again, there's 10 features that are extracted for each nucleus in an image. And then there's 3 statistics that they calculate for each of these. So we end up with about 30 features per image. So the first thing we need to do is get the data inside Python so that we could do stuff to it. So the way that we do this is we create a path to the CSV file. And this is basically the path that leads to that CSV file on my Google Drive. So I give it a name, which is BCA Wisconsin path. And then this function here takes in that CSV file and reads it into a variable in memory. And this is called a data frame. This is sort of like a table in Python. So I'm going to run this, and then I'm going to run this function here. This is, in programming, this is a method of the data frame object. And so I'm just going to run this. And what it does is it prints out the first 5 rows of the data set. And so I've got my ID column here. I've got my diagnosis labels, and I've got all my data loaded up here. This is a deceptively simple step. Being able to ensure that your data has been imported properly can save you a lot of headaches down the line. I can tell you a bunch of embarrassing stories about people loading up the wrong CSV file and getting all kinds of weird results. There's a bunch of different methods that you can call. For example, you can run this info method. And this info method will allow you to sort of summarize the data that's contained in your data frame. So Pandas is pretty smart. A lot of times, if you have a clinical data set that you've obtained from someone, there will be maybe patients that don't have all of their features. So if you don't know the output or the outcome of a patient and your target is the outcome label, that will just be missing or blank, or it'll have a value there that is not what you expected. And so these kind of summary methods allow you to quickly see whether or not everything is as it should be. So one quick check here is there's a column here that tells you how many rows in your data set have data in them. So there's 569 rows or subjects in this data set. And if we look down this column, every feature that we're looking at is fully fleshed out with some kind of data. And if we look at this column, all of them are float 64, which is just a type of number. So it means that somebody didn't type something weird in the area mean column. So we know that everything in here has been interpreted as a number, which means we could use it as a feature value. If somebody put like not available in text, that would show up as a different thing in this summary statement. So this is a good way just to check again that your data is what you expect it to be. Okay. So one thing we would like to do is verify that the diagnosis column, which represents the label that we're trying to predict, is well formed. So we're going to handle some categorical variables. Oh, actually, this is for the targets. In addition to the feature values that we have here, sometimes you'll get features that are not numbers. Features like if one of the columns was blood type, for example, or if you had a feature that was binned into low, intermediate, and high values. then that would appear as one of these columns. Those aren't numeric, and so we have different ways of dealing with that from a machine learning perspective. In this particular data set, we don't have any of those cases. So I just kind of put the code here for how you would handle these. One is converting them to ordinal numbers, which means if you have low, intermediate, and high as your feature values, you can convert them to 0, 1, and 2 because they can be ordered, so they're ordinal values. If you do have something like blood types, then you would use something like one-hot encoding to turn them into numbers. Basically, what this does is it creates a set of new variables that are binary, so either 0 or 1. So this allows you to put these variables into your machine learning pipeline. Okay, but again, we don't have any of these. We don't have any of these categorical values or these ordinal values, so we're just going to move on. And then the last thing we want to do is convert our diagnosis label to a number. So our diagnosis label, which is just M and B for benign and malignant, we're going to convert that to a 0 and 1. This is what we call a binary class problem. We only have 2 classes. Every sample belongs to one or the other class. So there's no samples that belong to both, and there's no samples that belong to neither. So everything is either a 0 or a 1. For this, we're going to use the scikit-learn package, which has a ton of information and functions and functionality for doing machine learning. So if you're interested in doing classical machine learning, I highly recommend that you use this package. The way in which all the code is written is very nicely formatted. It's very sensible. Once you work with it for a while, it's very easy to get going with new stuff. So this has a method or a class called label encoder. And so what we do is first we pull out the column corresponding to the diagnosis column into its own variable. We create a label encoder, which is just blank. It's just an object. And then we fit the label encoder to that diagnosis category. So what I'm going to do is I'm going to run this. And then I'm going to add a code cell here just to show you what this has done. So diagnosis category is a data frame, or it's actually a series that has just the diagnosis label column. We took that, we fit that data, the label encoder to that data so that the label encoder knows, okay, we've got an M and we've got a B, and that's all that we have, and we assign a number to each of those. And then the transform basically applies that label encoder to the category label. So we get diagnosis label, right? So now we just get a bunch of 0s and 1s, which corresponds to benign and malignant. And then we can do df.head to look at the top couple of samples. And we can see that now we have a column label here all the way on the end that says diagnosis label, and this has our 1s and 0s. And actually, I think if I tell it to print out the first 20 rows instead of just the first 5, yeah, we get a benign case down here. So we can verify that benign is 0 and malignant is 1. And so this is the target that we're going to use for our classification. Okay. Now, an important concept in machine learning is the separation between your training set and your testing set. So when you report your accuracy or your performance, you want to make sure that you're evaluating on data that you've never seen before. So the idea behind this is you have one set of data that's going to be used as the model training or model creation. And so that's what you're going to do all your experimentation on. And then you have a subset of your data which is not looked at for training, and you just report your accuracy on that whole data set. This is to make sure that your data or that your models can generalize to new data. So the idea or the use case is that you get a new patient into your clinic, they generate some data for you, you should be able to predict their outcome label or their target label without ever having seen their specific set of features before. So in this case, what we're going to do is what's called stratified sampling, which means we want to maintain the ratio of benign and malignant cases in our data set. So this is what stratified subsampling does. And again, the scikit-learn package comes to our rescue with a stratified shuffle split. What this will do is randomize the list of values or the list of data, and then chop out a percentage of that data while maintaining the class balance in each of the data sets. So what this will do is create a stratified shuffle split object and then apply it to our data frame using our diagnosis label as our splitting object. Okay. And what I have down here, so now we get two new data frames, training set and testing set. And what I'm going to do is I'm going to demonstrate the number of each class in the overall data set and then in our training and testing, just to verify that the number of samples in each of these is the same. So our overall class ratio, 63% of our samples are benign and 37% of our classes are malignant. And then in both the training set and the testing set, that ratio has been maintained. And this is important because, again, we're trying to generalize. So if in the universe there's twice as many benign cases as malignant cases, then when we report things like accuracy, we want to be able to contextualize what that accuracy means. And Abhir mentioned this before, depending on your classifier, you can handle balanced and unbalanced classes differently. There's a bunch of different strategies. You could over or undersample. In our case, we're sort of going to ignore this problem for now. And we're just going to use the ratios that are in our training and testing set. But it's important to keep this in mind, especially for rare diseases where your training set might only have a couple of samples of your target class. And the other thing to note here is that this separation into training and testing is what adds to the burden of data set sizes when you're looking at how many patients you have to do analysis. And data scientists typically want to see data set sizes in the hundreds, because if you only have 50 cases, right away you're going to lose a bunch of them to this train test split. And then depending on the number of classes you have, each class has a small number of samples in it. So if you want to do machine learning, you really need to have quite a few samples so that you can maintain this splitting. Okay, so the next step is now we've got a data frame. We've got two data frames. We've got a training and a testing set. And so now what we need to do is clean up the data set to make sure that we don't have any missing values, we don't have any categorical values, and we need to make sure that the data is scaled. And luckily, because we're using a data set that has already sort of been curated, we don't really have to worry about these steps. Again, I have these code cells in here just to show you how it would work. But this is more applicable to clinical data sets where you're going to expect that data is not going to be entered correctly, or there's going to be data missing, or you're going to have multiple values that represent the same thing. For example, in benign and malignant, a lot of times you'll get a capital B and then a lowercase b, which are considered different labels by Python. Or you'll get the word benign instead of just a B. So this will sort of help you. This data cleaning step is to make sure that those little things are smoothed out in your data frame. In general, we want to be working on the data frame for training, and then we want to calculate all of these different transforms that need to take place, and then just apply them to the testing set. So we're not going to use any testing data to figure out these little problems. We're just going to work on the training data here. And then we're also going to pull out the testing values and labels just so that we could use them later for our evaluation. So missing values, again, we don't have any missing values here, but there's a couple of different options. You could drop a sample that has missing data. You could remove an attribute that's not complete if you only have a couple of samples that have a particular set of features. You could just remove those features. Or you could set the missing values to some data point. This is called data imputation, which is a whole field in and of itself. If you have a large amount of data, you can get away with dropping samples that have missing features. So if you have thousands of samples, then you're not really going to miss one if you drop it, if it's not contained all of its features. There are some classifiers like decision trees that will allow you to just work with missing features seamlessly. Or if you have a lot of features and the feature with the missing value is correlated, then you can consider dropping the feature because you might not need it. Okay, so these are different strategies. Again, we don't have this in our data set, so we're going to skip this. Your data should generally be scaled, and there's different ways of doing that. You could do this through min-max scaling, so you can scale your data, your feature values to be between 0 and 1 by subtracting the minimum value and then dividing by the difference between the maximum and the minimum. Again, there's a transformer for this, and you can give it a range, so you can tell it which one to scale to. And then there's standardization, which means that you scale your features to have a 0 mean and a unit variance. You're not bounded in this case, so your data values could be less than 0, they could be less than -1, they could be greater than 1, but these are less affected by outliers. So if you have a feature value that has a lot of outliers, min-max scaling is going to sort of crush everything to one side of the 0 to 1 range. In our case, what I'm going to do is I'm going to use a pipeline. And this is I don't think I'm going to have time to go too in depth with this, but a pipeline is a specific feature for scikit-learn, which allows you to chain together these different methods, right? So if you have a set of data transforms that you want to apply, and even for classification, you can make a pipeline that does classification as well. And the pipeline basically strings together all these functions so that you can make sure that you just have one object that you train using your training data, and then you apply it to your testing data. So in this case, we're going to use standard scaling, and we're going to create a pipeline for that. And then we're going to fit the pipeline to our training data and then use it to transform our training values. And so we have training values transformed here. Okay, I'm going to stop to take a drink of water. If anyone has any questions, Andrew, that you think I should address.
I've been grinding through them. You just keep chugging along, Scott.
Okay. The semester is over, but I'm still giving lectures. So. Okay.
Somebody has got their hand raised, Yunnan, but obviously we can't unmute them. So maybe you can ask them if they have any specific question, Andrew.
Yeah, I mean, just add the questions to the Q&A. I've been going through those.
Yeah.
So you can find the already answered one and the answered.
I see that they have been allowed to unmute themselves if they wanted to. Yunnan, would you like to go ahead, ask your question if you have any? You can unmute yourself. Okay, maybe they don't have question anymore, in which case we can carry on.
Okay, sounds good.
Oh, there is one question I can see here. Didn't work out of the box. I don't know if people are still facing that problem. A bit late, but I just noticed that.
So the code is not working out of the box?
The data directory pointed to classes B4322021 and notebooks.
Yeah, that was a typo that I noticed last night. So if you looked at the notebook ahead of time, you may have noticed that this data directory was something different. It still worked on my end because I have access to my own drive, but this is really just the idea behind this is that you want this variable to point to wherever your data is stored. Because we're running this in a collaboratory notebook, I've mounted my collab notebook here. If you have you'll probably have a different arrangement of folders. So if you have copied over the notebook as well as the CSV file, then you will need to modify this to be whatever folder you've copied it to. So I think everyone's Google Drive sort of ends with my drive. And then after that, you could set up, this is my particular path on my Google Drive. So you'll need to edit this line to match whatever folder you copied the data into. If you want to know where it's looking, after this, if you type under here, if you add a code cell, type out print BCA Wisconsin path. This will print out the path that it expects to find the CSV file. So you can compare this with your own Google Drive sort of path up here and make sure that it matches. If it doesn't, then what you'll end up with is you'll get an error here. So if I try, for example, to df temp equals pd read csv blah.csv, it'll give me an error that says no such file or directory. So if you're getting this error, it's probably due to this variable right here. Okay. All right. So we've got our data. We've got it split into our training set. We've scaled it. Now we want to start looking at it. So data exploration is really important. It's usually one of the first things that you could do. We're going to create a copy of our data set just to make sure that we don't do anything strange. And the only thing we need to do is drop the diagnosis label and the diagnosis column. So data copy head is just a data frame that contains all of our feature values. So the first thing we'd like to know if any of these features are correlated with one another. So for example, we might expect that area and radius might be correlated with one another, as well as perimeter. So we want to be able to identify these and remove them, because a lot of machine learning algorithms expect that there's going to be relatively low correlations between your feature values. So given a data frame, there's a really nice method. It's just called core for correlation. And you get a matrix of values that lists the pairwise correlation between different feature values. So if I print out our correlation matrix, you can see here that it will print out for you the correlations between different feature values. So for example, perimeter mean is perfectly positively correlated with radius mean, which means as perimeter goes up, radius goes up, which makes sense for nuclei because they're circular, right? Area is very close to perfectly correlated with radius, and so on. Everything on the diagonal here is ones because every feature is perfectly correlated with itself. And anything that's negatively correlated means that as one feature goes up, the other one goes down. So what we'd like to do is find these pairs of features like area and perimeter that are very highly correlated and remove one of them. And this code is a little bit complex because I tried to pack a lot into a small area, but this basically just looks at the top of this matrix here and identifies all the highly correlated pairs of features and then removes one of them. And it actually prints out which columns it's going to drop. So it's going to drop perimeter mean, area mean, perimeter, standard error, area, standard error, and so on. And then this actually performs the dropping of those columns. And so when we look at our data copy now, we're left with the feature values that were uncorrelated with all the others. Okay. Now, having done that, we would like to visualize some of our features. So we want to see if anything pops out that might be an interesting set of features to look at. So just like we saw before with the probability density functions and those histograms, we want to be able to plot those to see if we can separate out our target classes, our benign and our malignant classes. So the first thing I'm going to do is just pick a feature. I'm going to look at radius because we know that malignant nuclei might be bigger than benign nuclei. So we're going to look at the radius mean. And this code here just prints out the histogram. And then all of this just adds a title and labels to the axis and then shows it. So this is what our histogram looks like. And we're not coloring this based on class. We're just printing out all of the feature values at once. You can put all kinds of different parameters to this histogram to change things like the bin size and the color and all of that kind of stuff. I'm not really going to go into that here, but you can make this look as fancy as you'd like. If we want to look at a different feature, all I need to do is type in a different name here. So if I want to look at texture mean instead and just rerun this, obviously if I was doing this for real, I would change this as well, but you get the idea. Oop, what did I do? Undo. Okay. Chaos
ensues in the middle of the.
I know. This was what I feared. All right, I'm going to leave that. I'm going to come back to that. I don't think we need that plot anymore anyway. So the next step is we're going to separate out our malignant and our benign classes so that we look at the separation between our classes in our histogram. It just saved the mistake I made, so that's good. So now we have a data frame for malignant cases, malignant samples, and a data set for benign samples. And it's taken a minute to run, so I'm not sure what's happening there. I really did break everything. All right, give me one moment. Let me just refresh. Sometimes this happens. You get these little hiccups. let me go through and run these again. So when you refresh, if you have to refresh, it reconnects to a new runtime, which means you have to run the code again because everything that was in Python's memory up until that point has been erased. So I'm just going to go through, and what I'm doing right now, just keyboard shortcuts, I'm holding down Shift and hitting Enter, and that will execute the code cell that you're on. So again, we create our path, print out the path. I'm going to skip this because that was my example from before. I run this again to make sure, okay, so the data frame is in Python's memory. View the info, make sure everything looks good. I don't think we needed to do anything here. We did have to convert the target to numeric. And we do have to split out our training and testing sets. Okay, let's just make sure everything is as it was before, which it is. Data cleaning steps. We didn't have any missing. We did do scaling using our pipeline, so I'll just execute this. There we go. And we calculated our feature correlations. Great, okay. Now we're back to here. Now we have our malignant and benign data sets. So now we want to plot out basically the same thing, except now we're plotting out two different histograms. This is really the only code that runs the histogram section. Everything else is for display purposes. So you can sort of ignore everything except these two lines. And this will take the malignant data frame and print out the texture mean value. So if I hold Shift and hit Enter, we get a nice plot that looks like this, which is similar to what you saw in the previous talk. I'm going to speed up a little bit because I'm noticing that I'm running out of time. We have about 20 minutes left. So this allows you to investigate different features to see whether or not this is a good feature to use for classification. So you can start to get a sense of how well your feature values can discriminate between your different classes. If I wanted to show a different feature because of the way that I've coded this, I could just type in a different feature name here. So radius mean, and then all of this code is going to adjust everything. Here, I actually went through the effort and put in a new display name. So it'll actually change the title for this. So if you're making a paper or a presentation and you're running a lot of code, this is really useful because now you could just rerun your analysis and drop the plot directly into your paper. Which I've done here. I did it by hand up top, but here's the same thing. Now looking at one feature value at a time is not super efficient. So we'd like to look at several at once. And there's some code that allows us to do that. So histograms are for one feature. If we want to look at two features together to see how they vary and how they might cluster out our data, then we could look at these scatter plots. And so here we have two features plotted on the x-axis and the y-axis. And again, we have our data points here. Again, each point here is a sample or a row, and each color corresponds to a class. And what you're looking for here is, are these clusters of points separate? Do they cluster out nicely, or are they completely overlapping? If they're overlapping, then that means that the features don't discriminate between your classes. If they are not overlapping, or if they're separate like this, then you can imagine that if you draw a line between these two clusters, then if a new sample appears up here, it's probably going to be malignant. If a new sample appears over here, it's probably going to be benign. And that's how you would do the classification. We didn't talk about linear discriminants because we ran out of time, but that's basically the idea. This is two features. You could obviously look at as many features as you want, but it's difficult to plot out 3 dimensions. So one way of doing that is to look at something called a facet plot, which basically just creates a bunch of scatter plots looking at different pairwise combinations of feature values. And this is something that's provided by a different library called Seaborn, which gives you this pair plot distribution. So here you could look at, each of these. This is a little bit hard to see. I'm just going to go down here. Each of these plots corresponds to a different pairwise comparison between feature A on the y-axis and feature B on the x-axis. And then instead of plotting a feature with itself, which would just be a straight line, it plots out the histogram of that feature or the PDF of that feature. So you can start to sort of pick out different feature combinations that you think might be useful for your classification problem. One way that we can try to look at high dimensional data in low number of dimensions or in 2 or 3 dimensions is through something called dimensionality reduction. And this is a big field. There's a lot of different techniques. I kind of illustrated a couple of the different techniques here. They make different assumptions about the data, and they require different amounts of training data to run. In some cases, they need labels. In some cases, you could do it in an unsupervised fashion. But essentially, we're just going to perform principal component analysis on our data. And again, using sklearn, we can do this using the same kind of named methods that we had before. In this case, I'm going to reduce the entirety of our feature data set down to just 2 principal components. So I'm going to run that, and then I'm going to plot a scatter plot of those 2 principal components. This is the unlabeled data set. So this is what the data looks like if we were just going to do unsupervised clustering. And if we separate them out into malignant and benign, then it looks like this. So this is, when I show these plots, we oftentimes get the question of what these axes represent. They are a combination of the feature values in high dimensional space. So if our feature set here was 30 features, then these components, these principal components, represent the dimension along the maximum variation along a dimension. So the idea is that if your data is able to be separated in high dimensional space, it should be separable in low dimensional space as well. And so looking at this gives you a sense of how all the features together can contribute to your classification performance. Okay, so this was just looking at the data and just getting a sense of what the features look like and whether your classification problem is doable. And hopefully by this point, you have a pretty good idea of whether or not your classification is going to work or give you high performance. So now you can get to the actual classification bit. Now, I have a bunch of code here that talks about how to create the histograms for naive Bayes that you saw in the previous talk. And so you could go through these and basically create the histograms, create the functions, apply the model and learn the model for different classes. So I have the code here for you to look at, but just for the sake of time and simplicity, I'm going to skip down to the cheaty way, which is using the built-in functions in scikit-learn. And this is why I encourage people to look at this package if you want to implement your own machine learning algorithms. So there is a class here that implements naive Bayes. So NB for naive Bayes. And then Gaussian is because it makes the assumption that each class is modeled by a Gaussian distribution. So if I go up here, right, in general, actually this makes the same assumption. Let me go up to here. So this is the actual histogram. In general, if you have a lot of data, you can, at a first glance, you could approximate this with a bell curve or Gaussian curve. That's not the case for all feature values. Sometimes you have different distributions that work differently. But for our purposes, we're going to model these as Gaussians. And so down here, this will create a Gaussian naive Bayes classifier. It will fit the data. I'm going to take this away. It will fit the data to our reduced dimensional data set. And it also requires the labels, so it knows which samples belong to which class. And then I can run this prediction to get a probabilistic prediction for each of our samples to see what it thinks the likelihood is that each sample is benign or malignant. Oh, that didn't work. Why didn't that work? Oh, this needs to be, I didn't create the domain, that's why. There's one of these cells that I skipped over that I should have run. Where is it? It's my domain value. All right, I will stop here for questions while I look for this thing.
Okay, Scott, apparently there is a question from Abdulwarith Akinchipo. If you want to pose your question here, you're welcome, Abdulwarith.
Was this in the QA?
No, he has his hand up. I've been doing the Q&A questions.
Okay.
I mean, I think if you just run like all the cells, you'll be okay, right?
Yeah, I ran the, I got the domain now, so I'm ready to go. Okay. Okay, so if there's more questions, you can pop them in the Q&A. I'll also, after this, I'll go back and I'll look through the questions just to make sure there's not something to add. So what I do here is I set up the min and max values of our domain, which is the min and max values for the features we're going to use. And then I create a domain just so that I can perform classification using it. So I'm going to, I ran that, so I have my domain. And then this, I hope. Yes, okay. So what this will do is this will give me a probability matrix where each of these is a different class. So if I look at the shape of this variable, what I've done is I basically classified the entire space, the entire feature space. So every point, every combination of features that could exist according to our training data is listed here. And then this Gaussian naive Bayes creates a probability for each of the classes. So in this case, we have two classes. So the columns represent class 1 and class 2, or in this case, benign and malignant. If we have more classes, then it would produce a probability for each of those. If you look at the values themselves, these two will add up to 1 because it's going to predict, you know, there's a 100% probability it's going to be either benign or malignant. So these probabilities are going to add up to 1. They're always going to be positive or 0 at worst. And you can see here that it's actually pretty confident in a lot of these samples. So this is e to the negative 30, so that's functionally 0. And then this is about 1. There's some rounding error that goes into these, so that's why they're weird numbers. But you could essentially say it's pretty confident in the classification. These 3 dots here means that there's a lot more values in between here that it's not looking at. One thing we can do, this is going to, yeah, I'm just going to run all these cells because I think I'm referring to things that I didn't run. So, okay, I'm just going to run these. Okay, so we got our probability density function. This is the probability of observing our first principal component given each of the classes. And then we look at specific feature values and the probability for each of those. We use what's called non-informative priors, which means we don't consider one class to be more likely than the other. Although, as we saw at the beginning, the benign class is about twice as likely as the malignant class. So we could adjust these numbers to reflect that if we wanted to. If I have time, maybe I'll do that. Okay. Okay, so this here is the output for each value in PCA1, which is just one of the principal components. This will give you the probability according to our histogram. So we have these bin counts, which is why this looks blocky, right? We have these bins that we've used to calculate the PDF for the training data. And what this, again, if you look at a single value on the x-axis, the value for the probability of observing the benign class plus the probability of observing the malignant class is always going to add up to 1. So these are sort of symmetric functions. If we had more classes here, you'd see more lines. But if you added them all up on the x-axis, you get 1. And so values that are below, you know, -5 or -3, whatever this is, are more likely to be benign than malignant. And I'm using the term likely very pointedly because it still means that you do have some malignant cases that have these feature values. But if you just use your first principal component, you're going to get those values, you're going to get those samples incorrect. So it's important to understand that there's a certain amount of irreducible error when you're using this approach, unless your classes are linearly separable, which means that you have completely separate blobs in high dimensional space. Okay, so we ran all of this. This is the same plot except here we've used the Gaussian naive Bayes function rather than doing it ourselves. And you can see that I think the colors are flipped here. Oh, these are for different feature values. Or no, actually, what happened here? Oh, right. So this trails off at a certain point because we don't have feature values that go down that far. In this case, the function doesn't cut off here. It goes off into the other direction. But you can see that there's a difference here in the colors. So now that we visualize this, we can actually create a grid of the entire feature space and look at what would happen if we classified each sample in that feature space. And so this gives us that dividing line between the benign and malignant classes that we were looking at before. So this gives us a sense of if a sample appears in the red area, it's going to be classified as, I think, benign. No, these are benign. These are malignant. So I think these are the malignant cases. So if a new sample has its feature values extracted, it goes through the PCA process and it gets plotted into this feature value field and it ends up over here, it's going to be classified as malignant. If it ends up in this blue, it's going to be classified as benign. And you could also see where all the outliers are, right? So we've got samples that are malignant in the benign area. We've got benign samples in the malignant area. But given the features that we have access to, this is the best that we can do while still maintaining generalizability. If we were to see a more complex classifier that kind of draws a line around each one of these and tries to perfectly classify this, it would basically just be memorizing the training set. And so that won't be as useful for new samples. Okay, I think I'm going to stop here because this pipelines discussion is a lot longer, but essentially you have access to this code. So if you want to look at the implementation of pipelines for classification, this will help you figure out all the little knobs and dials that you can tweak to try and make this classifier more efficient or better. You can sort of automatically run a lot of experiments very quickly using the pipelines interface. So that gives you the option of doing that. So yeah, if there's any questions, I'm happy to take them. Also, if you would like a longer sort of discussion about this or a longer tutorial, I'm happy to do so. You can get in touch with me or with Nasir and we could put something together. So if you'd like me to do something like this and go more into detail about these different aspects, we could certainly do that. I teach a whole semester long class on this stuff, so that there's a lot to talk about that I'm sort of glossing over. But this is kind of how those classification results are generated that you saw earlier in the day.
Thank you for the extremely helpful tutorial, Scott. You covered a whole lot of stuff in just under an hour, and it's I'm sure it's pretty useful for everyone. And Andrew has been doing an excellent job at promptly responding to all the questions that people have. So, okay, we had one question, and it was thank you, Scott. So, yeah,
You're welcome.
I'll answer that one as well. Don't worry about it, Scott.
Okay. If there are any further questions from the audience, we'd be happy to take them.
Yeah, fabulous stuff again, Scott and Andrew. Thank you very much, Amna, for chairing the session as well. It's been really useful. We can already see someone asking, is your whole semester class available online? Is there a YouTube link you can send us?
So actually, one of the things about the pandemic is that it has forced me to act on my long-running desire to start recording my classes and putting them up. They're not up right now because the class just finished. We're actually putting in the grades this week, but I will. I have to find out if I'm actually allowed to put them on YouTube, and if I am, then I will certainly try to do so. And like I said, if you'd like a more sort of interactive, smaller group discussion like this, let me know, because I have a lot of examples that I could show. And if you have specific questions about computational pathology, sort of application of this stuff, I'd be happy to go through that.
If you don't make them available on YouTube, I suspect that we might call you back sooner than next year, Scott.
Great, excellent. I would love to do it.
Okay, we have, there is one more question here. Amna, would you like to moderate that?
I think Andrew is already in the process of responding to it, but there is a question that in your everyday, which software do you use to extract the image features? So,
so that's a great question. So there's a couple different software. Some folks have already talked about how to do this for whole slide imaging. So software like QPath is really good if you have a whole slide image that you want to analyze. They have some functionality, some plugins for extracting image features. There's also a piece of software called Cell Profiler, which is put out by the Broad Institute in the United States. It's also open source. I don't think it works as well with whole slide images, but if you have patches, what it does is it allows you to set up an image processing pipeline. So if you want to crop an image and then run a filter on it and then look at the output and then segment that and try to calculate features from that, it allows you to set up those pipelines. What's really nice about it is that that software uses Python underneath. So if you wanted to then give that to your engineers and allow them to work with the pipeline that you've set up, you could do that. But it's a nice sort of point and click interface for doing different image feature extraction routines. For most of our stuff, we code it ourselves just because we're familiar with the programming. But if you want to get started as a sort of a very quick trial run on some patches, you could use that software.
Yeah, I think just one of the reasons why we end up going in and not using available software is because once you have to basically start interacting with each image individually, you're really limited in your productivity. So, I mean, Scott and I both use Python, and the main reason is, it doesn't have to be Python, it could be MATLAB, whatever it is, but we use scripting languages simply because when we need to analyze 2,000 images, you can't do that in a user interface, right? You write code and you send it to a high performance computing environment. So our application and the way we do it is a little different than I think what we would suggest pathologists do if they're interested in kind of getting a feel for that. Also, in response to one of the questions in this question here, maybe I'll click answer live. I can put in, there's tons of free courses available on Coursera as well. There's 4 of them that I suggest. They're kind of more full-bodied courses that if you're interested, I think at least the theory of them and seeing some examples. So I put them in order of increasing difficulty, where there's an image analysis course, AI for medical prognosis, which is really kind of high level, machine learning, which has covered some of the practical stuff Scott's talked about and some of the other stuff from the theory part of that, and then the deep learning component as well. So this is some of the stuff that we use to train our students. It does, I will say, in some points get very, very complex, likely more complex than a pathologist would need, but would still be good just to kind of see and become familiar with that sort of thing. So that's a good place to start. Unfortunately, they're not pathology specific, so they're much more general, but at the same time, I think that might potentially further motivate you when you see that, okay, this isn't just applied to pathology. A lot of the stuff that, Scott's introduced and we've spoken about today, you could also apply to imaging. You can also apply to genomics. You can also apply here and here and here. And once you kind of have the idea of training and testing sets and how do I validate this correctly and all these things kind of click into place, you really have the ability to translate between different data domains.
thank you, Andrew. I don't think we have any further questions. The talk has been really helpful. I'd thank you again for the extremely helpful tutorial, and I'm sure people would benefit a lot from this.
Thank you.
Okay, so
I was just going to suggest a couple of minutes break before the panel, but I'm going to leave it to our moderator to decide what he would like to do. Again, thank you very much, Andrew, Scott, and Amina for this session. This was really awesome.